Trigonometry plays a pretty big part in squaring a foundation. It's in the word square, which can be defined as 4 equal sides with the summation of the angles equivalent to 360 degrees. So side 1 is the same. I denote all sides being the same with 2, almost like an equal sign on every line. And I know the total of this, all these 90-degree angles, 90, 180, 270, 360. For the sake of example of building a house, we're going to use a trig function. Trig function, which basically is a fancier way of saying we're using an equation of a line and we're plugging it into another equation of a line. Because if you could see that if I just went like this down the center, well, now instead of a square I have 2 triangles. So if I divided this equally, what would you say that the area of a triangle would be? It would be half of this. So area of a triangle, I'll denote that with a triangle, is equal to 180 degrees. So now the trig function is set up almost as the trig function is set up in terms of your space. So for this case, let's say this was your back corner. I would pull down this wall. I'd pull down this wall. Within these 2 measurements, I could figure out theoretically what this diagonal can be. So moving on, we go on to Pythagorean theorem. I'll tell you the equation now, and I will do the explanation later. So in order to explain this equation, I have to basically summarize it with a descriptive picture to understand how these came to be. Maybe it's not important to you, but it might be important to some to see why it is the way this way. So I want you to imagine a square within a square. And then with the corners touching each side of the square, almost like a diamond. If you were to just rotate this square 90 degrees this way, it would be like a diamond. So like this. Which, it doesn't have to be a perfect diamond. It's arbitrary, these 2 points. But let's just say, for example, I labeled this center square C. Well, in order for this to find the area of the triangle, I'm just taking this line. I take this line and multiply it by how many segments I'm going this way. So effectively, the area of a square equals, well, in our way of speaking, it's length times width, or y and x. So I'll just write length times width. So back to the picture. We have this area of a square C, the shaded region. Well, we can label all its sides because we know it's equal as C. We'll turn it to whatever the number is of our house. Let's say, again, this is our back corner of our foundation. I know this, I know this. I can figure out C. with these two variables. I know the equation of a line or a triangle. It actually is half the base times the height for most cases. But anyways, to further on with the derivation of this equation, now you're basically just closing these two outer triangles on each other. And so now the total area C is defined by the empty spaces a squared and b squared. So in theory, we are summing up these two squares now that are created as the voids that this creates when these triangles are met up. And basically that C value is in terms of area, but that's why we square root it at the end. So to finish this equation off, it would be, in simplest terms, C is equal to a squared plus b squared all square rooted, because the opposite function of squaring something is square rooting it. If you multiply it by itself, the square root of itself is dividing by itself. So that was just a little side note to how the equation came to be. So let's put it into use. Let's say, for example, this is your foundation. Let's say it steps in a bit at the, it's called the right, the front. So this will be the back of the house. Back. And this will be the front. So when I show up to a job, first thing I need to do is establish the points. I mean, after the concrete's been chipped away at, and so you're ready to make good marks. I use the back of the house or my longest wall. Most people will hook on their tape and see their closest value that they can get out of 3, 4, 5. 4 would be the longest wall in this case. So I would go 4, 8, 16, 20, 24, but sometimes you miss that little part there, which can actually end up you if you were to be those kind of guys that would project that line. Because if this was mistakenly done or whatever, and you start pulling a tape this way, and it's a gradual mistake. So it actually ends up hurting you if you don't know the overall size of your house to begin with. So when you show up, you snap your longest wall. That's your first, whether it's brick or siding, you try and cheat it as much as you can to make it work on both sides and all the way in between. And then from there, you can check how square your corner is by knowing this dimension, and then you know that the dimension over here is limited by the brick or the siding on this side. So you make your mark, you get a measurement in between here and in here. So you put that into your calculator or your equation, and then you're determining this. So I make the mark here, Buddy holds my long tape here, I have the mark out here, and then it's just an arc. I swing an arc on this corner. And the connection of this point and this point, we already established. And now the connection and connection here is the same exact number, depending on the length to the front. You see how that works? And then boom, I know that everything I pull off of these lines, whether it be this way or this way, is all going to be a perfect right angle. And it makes building a lot easier when everything is square. So really quickly, I know that this back wall, where the corner of that square is like my starting point. That's the back corner of the house basically. And then this wall comes this way to here, and then this is my square wall. I'm gonna run this line all the way. So basically I'll take this number outside to outside, or get kind of close so you're not fucking up the marks when you go to snap 5.5s. And then I just take the longest measurement I can. So if there's concrete out here, that would be perfect. Like if I could drop this house actually ended up, this is the garage wall, and the floor ended up cantilevering over here onto a pad or something. Yeah, it was a lot of work. Anyways, so yeah, that's what we did. We just, actually in this case, the concrete ran out to here, so, you know, I was close enough if I was here or whatever, but this pad came out to here, right? So I snapped this line all the way out to this porch right here. So if I'm off like this angle, I'm not really worried about that. This just gets you kind of in the range, so you know your walls are dead nuts all the time. And then, you know, when it goes to leveling and bracing, it's you could basically nail it right on layout. That's what I found was the easiest way, assuming your floor was leveled and the concrete guys. So anyways, just for example, I used the same number, or the same functions up here, the rise, the run, and the diagonal. So basically, I'm just plugging this as, like, for example, the rise, and this one would be the run. This is what I actually did. So I did whatever, 10 feet this way, and then this would be like 15 and a quarter. Let's just say 15. 10 feet rise, and then what did I say? 15 feet run, diagonal. So 18 5/16. So basically, I guess I want to hold me back here. I make this mark from here to here at 15, this mark at 10, and then this should be 18 feet and a small 5/16. Simply put, this is your diagram. You're going to find the overall area of all of this triangle, and then I'm going to subtract this. And remember, we're not using numbers, we're using variables to make the equation theoretical and not empirical. So if you look at it, this triangle, or sorry, this square is just arbitrary. I can make this square even. I can make these points go this way, whatever. It doesn't really matter because we're using variables and arbitrary marks on the earth, basically, to establish square. So simply, if I just remove this triangle, square, or whatever you want to call it, put it over here for a sec, I push these two together, I'll get something that looks like this. These are just simply the A values, and then these are simply the B values of the triangles that we made when we divided or added these together. That leads to this equation. It's called sum of squares, and it'll end up working out to, this is called the sum of squares. That's the main misconception that people get, is that these are theoretical distances, when really this was all theorized out of areas of squares. So looking at this, for two equal squares, rectangles are created. After rearranging shapes added to new sections, simply remove the two squares comprised of A and B, and then that is your final equation. You're basically finding the difference between this whole and this in the middle, based off of your two lengths A and B.